Good day, everybody, and once again we are back together. So today we're going to be looking at the conversion between rectangular form and polar form, and also the other way around as well. So if you haven't subscribed, please just make sure you're part of the family, right? And click on that subscribe button. Right, so we've actually quite walked the journey quite a bit, right? In terms of complex numbers. Now, just to quickly recap, what we had said is that whenever we are given any complex number, right? So there it is, we've got a plus bi, right? So remember, what do we have? We've got the real part as well as the imaginary part, okay? Right, now what we said is that we can actually express this, in the form of a graph. And in this case, we refer to this graph. In this case, I want you to please just note. So let's say there is our Z over there. And what this means is that these are the real axes and these are the imaginary axes, right? So these are imaginary axes. So what this simply means is that A would be the value of that complex number along the x-axis, right? So that's our A value. So which means, let's say that would be A over there. And B in this case would be the value of y. Okay, so this is along our vertical axis, right? That is the imaginary axis. So that gives us the value of B over there. Right, now what we had said is that we can calculate the modulus, right? Meaning that this is the distance. So simply put, the distance of this line from the origin all the way up until we get to that complex number. Right, so we can calculate the modulus by simply saying, well, the modulus will simply be the distance. So that will be the value of a squared plus b squared. Otherwise, we did say that you can express these as x-axis. We know those are the real axes, and these would be the y-axis. And so the modulus simply becomes, in this case, the square root of x squared plus y squared. And we know we get this from the Pythagorean theorem, right? So that's plus y squared. Okay. Right, so this is how we express the modulus, okay? Right, so what I want us to do today is we're going to be juggling between, the polar form, all right? And I'm going to tell you exactly what is the polar form as well as the rectangular form. Now, when we look at this format that I've just given to you, A plus BI, we call this the rectangular form. And I showed you in our previous video, why is it that we refer to this as the rectangular form? Okay, right. And it is essentially for this reason that when you think about it, so A is along the x-axis, right? And B is along the y-axis. So if you take that, it kind of creates some form of a rectangle, right? So we call that the rectangular form. So you need to be able to convert from rectangular form into what we refer to as polar form. Okay, polar form. Now, what is polar form? This is also what we refer to as the modulus argument format. Okay, now, quickly just to also recap about what we've done. So we also call this the modulus argument form. All right. So in this case, I have shown you how to calculate the modulus of a complex number, and in this case, we can now look at the argument of it. Now, how do we look at the argument of this? We said, well, simply put, the argument of any complex number would be arctan, right? Let's switch that off. Otherwise, it will keep giving us issues of y over x, right? So we can always find out what is the value of the angle, right? And what is our argument? We said that's the angle of elevation between the real axes and where your complex number is. Okay, right. So there it is. That's the argument, as well as we've got the modulus, which is our r value, in this case, the distance from the origin to our complex number. All right, now let's quickly go for it. Okay, now suppose that we're given, right? So something that would be given to us, in fact, before I go into something that's given, I just need for us to recap quickly. How is it that we get from polar form, or rather from, from rectangular form to modulus argument? So remember, we've now calculated the modulus. We now learned how to calculate the argument. So what it simply says is that if I take x over r, right, this would be equal to the cosine of theta. So if you think about it, so if you think about cos of theta, that's adjacent, which is x, over r, that's the cosine of theta. So x over r is cosine of theta. And so in this case, that means that if I want to get the value of x, that will be r the cos of theta. Or you can say that it is the modulus multiplied by the cosine of the argument. Okay, but similarly, so we can do the same with sine. So that's y over r, that's equal to the sine of theta. So that means that y is equal to r, the sine of theta. And in this case, that means that when we want to express y, that would be the modulus, the sine of the argument. Okay, right. So that is how we quickly look at it, right? But now we can move from one to the other. So suppose that I give you, all right, if we had in polar form, there it is, if we are given, right, so this would be, oops, let's do this. Okay, so let's say, just for argument's sake, this would be the square root of 3, okay, root 3i, and let's say that is going to be 1. So remember, we can express this as a complex number. This is rectangular form. So in rectangular form, this complex number is, right, remember we always start with the real part, okay, over here. So that's 1 plus, in this case, that's still within the positive axis, that's square root of 3i, okay? So that is what it looks like in rectangular form, right? But now, how do I express it in the modulus argument form, or in polar form? So firstly, we said we're going to calculate the argument. So z, that's x squared plus y squared and the square root of that. Okay, so we are going to take x squared. And by the way, that's in the first quadrant. So that's x squared, that our x is 1. Our y is square root 3. And so that gives us 1 plus 3, which is 4. And square root of 4 is equal to 2. So the argument, or rather the modulus, is equal to 2. And in this case, if we want to find the argument, so the argument would be equal to the arctan, that's y over x. So y is our root 3 and x is 1. So that's the arctan of root 3 divided by 1. Remember, that is y over x. So now I can find out what that argument is. Shift the 10, okay, shift 10 of square root of 3, right, and we get 60 degrees, okay? So now, to write it in polar form, and please, I want you to note this very carefully, ladies and gents, right? So I've got the argument, but I also have now the modulus. So meaning that if I want to write it in polar form, I'm trying to show you where I was going with this, right? So this is what it would look like in polar form. So Z, okay, would be equal to the modulus. In fact, let's write it as R. So this would be R, the cosine of theta, plus I times the sine of theta. At university, they usually call this the RCIS method, okay? Right, or RCIS. Okay, RCIS. So if you think about it, it's cos, imaginary, sine, okay, of theta. Okay, so Z would be R cis theta. Okay, so in this case, this would be what the polar form of it would look like. So what is our R value? That's 2. The cosine of our argument, we said that's 60. I multiplied by, oh, and by the way, sorry, I forgot to put that in brackets over there. Okay, so I multiplied by the sine of 60. And of course, this is what it would look like in polar form. Okay, and in this case, you can actually continue with it or simplify it if you want to, but this is what it would look like in polar form. Okay, right. Now, ladies and gents, I want us to do the following. Okay, let's take an example. Let's take another example, and we're going to jump into some exercises, right? So suppose I give you another graph as well, or rather, let me say, let's give you another complex number plus 6i, okay? And I would like for you to write this in modulus argument form, okay? Right, otherwise called in polar form. So what are you going to do, ladies and gents? Right, so firstly, what would it look like? Right, both my x and y are positive. Let's draw it. X is 2. That's 2. And y is 6. Okay, so let's say it looks something like this. Okay, I know that that's 2 over there. And that would be 6 over there. These are my real x's. These are my imaginary x's. Okay, and so that's where I get the 2 plus 6i, right? Now, that means that I'm going to get the modulus, or R value. Okay, in fact, let me write it as R, that's square root of x squared plus y squared. That's going to be x squared is 2, y squared is 6, and so that will give us 4 plus 36, and that gives us the square root of 40, right? Now, if you think of 40, that would be 4 multiplied by 10. Okay, just to simplify it. So that's 4 times 10, which would give us square root of 4 is 2. So this would be 2 root 10. Okay, right. So that's what it would look like. And of course, we want to also find out what the argument is, all right, meaning the angle. So I am going to take, it doesn't really matter whether you take 10 or sine. Let me take cosine of the argument, right, just to show you. So that's going to be adjacent. So that's going to be x. Remember, the argument would be the angle that is here. So that's x over r. Okay. So that's going to be x divided by r, which is 2 root 10. Okay. Right. So theta would be the arc cos. Of course, you can cancel those two out. We've got 1 over root 2, or 1 over root 10. So this is the arc cosine of 1 over the square root of 10. Okay, and let's find that value. All right, and I get a value of 71.6. Okay, you can say 57 if you want to. If that's given in 2 decimal places, going to just leave it as that. Now, let's write this in polar form. Now that I've got the, the modulus as well as the argument, so now I can write it in polar form, okay, or the modulus argument form. So how does it look like? So that means that z, we said that's r cis, right? R cos theta plus I sine theta. Our R value, 2 root 10 into cos 71.6 degrees plus I, the sine of 71.6 degrees. Right, ladies and gents, that is what it looks like. Okay, so I want you to take the following examples. Actually, exercise rather. And I want you to do exactly the same as I have done. Okay, just like we used to, we are going to, I'm going to do some with you. Okay, so I want you to write the following. Following complex numbers in rectangular form. Right. Okay, so this, I want you to write the following in rectangular form. So if we're given in polar form 2 into cos 45 plus I sine 45. Next one. 8 into cos 75 plus I sine of 75. All right, now let's quickly try to do that. Okay, how are we going to do that? Right, so we're going to say for these ones, that means that our A value, that's 2 cos 45. That's the real part. Okay. That would be 2 cos of 45. And the imaginary part would be 2 sine of 45. Right, and you can work it out. And by the way, cos 45 is it's a special angle. Okay. All right, so that's 1 over root 2, or you can say root 2 over 2. Okay. Yeah, there we go there. So which means you are simply saying that's 2 into root 2 over 2. And again, the same is true here. Sine 45 is root 2 over 2 as well. Okay. And you'll notice that the 2's cancel and you're left with root 2. And you're also left with root 2 over there. Now let's write it in polar form. What does it look like? It means that in polar form, z would be equal to the square root of 2 plus I root 2. Okay, so that's what it would look like. All right, so this one is a little bit easier. Of course, you can always convert as easily as possible. Okay, you can do the same with this one over here. Write it in polar form, or rather, write it in rectangular form as it is given in polar form. Right, now let's take the next exercise. So exercise 2. This is where I'm going to give you some more exercises, right, for you to complete. Okay, so I want you to write the following. Okay, in polar form. Of course, we know now that it's also called the modulus argument format. Okay, right, so I want you to do that for me. And if possible, please try to draw the graph as well. Okay, so where it would lie and so on. Right. Okay, so quickly, how would we go about this? I'm sure you've got this by now. I'm only going to do A with you, all right, and the rest you can do on your own. And by the way, I forgot to just write down the square for this one. Okay, so Z, know that square root 3 plus I. So what do we do in this case? We identify our value for X as well as for Y. So X is equal to root 3, Y is equal to 1. So R would be the square root of root 3 squared plus 1 squared, and so that would give us 2. So R is equal to 2 over there. And of course, we need to find out what the argument is. So we found out in this case what is a modulus. So the argument of Z, that would be the arctan of Y over X. So that's 1 over root 3. Okay, and I believe that should be 60 degrees if I'm not too wrong. Square root of 3. Oh, it's 30 degrees actually. So that's 30 degrees. So let's write it down in polar form. Remember R cis. Okay, so in this case, Z would be R, that's 2. Okay. C, that's cos of 30 plus I, sine of 30 degrees. And that's what it looks like in polar form. And ladies and gents, I'm going to leave it here, right? And I'm going to ask, and by the way, I had said that please try to draw this, okay? The examples that I'm doing are in the first quadrant for now, but of course we will explore with having them in different quadrants as we go along. Right, so our x value was root 3, so if we said that's square root of 3 over there, okay, square root of 3, and you've got 1 over there. Okay, so there it is over there. So z is 1, rather square root 3, that's the real axis, plus I. Okay, that's 1 there, that's root 3. These are the real axes, these are the imaginary axes. Okay, right, so ladies and gents, that's how you would actually write that down in polar form. And please remember this because we are going to be using it quite extensively. All right, so for now, I'll leave it here and I will ask you to continue with the exercises, and I will see you guys again next time. I hope that you've been able to attend, to actually comprehend, what we are doing. And you are going to recommend even more of your friends to watch our channel. From me for now, I'll see you guys next time. Sharp, sharp.